Hello and welcome to the next lecture in this course on pattern recognition. For the last few classes, we had been discussing ideas from statistical learning theory and how one gives performance guarantees for learning algorithms, or how one can bound the generalization error of a learning system. Specifically, we have seen the VC theory. So, just to recap in two sentences, we looked at some ideas from statistical learning theory, and the basic thing that we have introduced is the so called risk minimization framework, whereby we essentially have a hypothesis space which represents some class of functions from the feature space to reals, and we evaluate each function or each hypothesis in terms of its risk, which is expectation of loss. So, we seen that the risk minimization framework gives a very good perspective on learning from examples, and it allows us to look at all the various learning algorithms under a single unifying theme. Okay. So, now that we have this perspective, now we go back and look at learning algorithms again, how to learn pattern classifiers from examples and also regression functions from examples, but this time we will be discussing things a little bit more in the risk minimization framework. Okay. So, we have already discussed, before we discuss statistical learning theory, we already studied some methods for learning linear classifiers and linear regression models. So, I will very quickly review, because it is some time, I will very quickly review the algorithms for learning linear models and then move on to learning nonlinear models. Okay. So, in the two class case, a linear classifier, as we know, is given by sin of W transpose x plus W naught. So, we have to learn this W and W naught to learn a linear classifier. This is a two class case. We also seen the multi class case, but let us not worry about it, it is just a review. Specifically, we also said, this is important for us, that we can think of a linear classifier also as W transpose phi x plus W naught, where phi x is some set of m functions of x, phi 1 x up to phi m x. So, this also, such a model can also be learned using the standard linear model learning techniques, as long as these phi's are fixed. So, if the phi's are prefixed functions, then this is still a linear model, because they are linear in the parameters to be learned. Phi's can be nonlinear functions of x, but does not matter, as long as they are fixed. The only things we are learning are the parameters, and the this W transpose phi x plus W naught is still linear in its parameters. So, linear models will still work. For example, we have seen how we can think of simple linear least squares method for learning any degree polynomial function. Okay. There are many algorithms for learning the W. The first and the simplest we considered is the perceptron algorithm, right? That is a simple error correcting type algorithm, and it guarantees to find a separating hyperplane if one exists. We are still discussing two class case. Actually, we showed that is, we proved a perceptron convergence theorem that shows that given any training set of linearly separable patterns, starting with any arbitrary initial W, if you run the perceptron algorithm, we ultimately stop after some finite iterations and output a separating hyperplane. Now, actually, this might be a good example of asking what is it that the statistical learning theory gives you. What the perceptron convergence theorem says is that give me any training set of linearly separable patterns, I will find a separating hyperplane that separates the training examples. So, if I give only 2 patterns also, it will find a separating hyperplane. If I give 20 patterns also, it will find a separating hyperplane. If I give 200 patterns also, it will find a separating hyperplane, right. So, let us assume the classes are linearly separable. So, all examples will also be linearly separable, but the separating hyperplane it finds on 2 patterns may not be same as what it finds on 200 patterns, right. Obviously, if you give very few examples, I may learn a separating hyperplane that separates the examples, but may not separate the pattern classes. So, the statistical learning theory that we have studied tells us how many IID examples we should have before we can be confident that the hyperplane that separates the examples will also do well on test data. For example, in this particular case, we know the family of hyperplanes in RD, the d-dimensional Euclidean space, has VC dimension d plus 1. So, as a thumb rule, we need at least 10 times d examples before a hyperplane that separates the examples is also very likely to separate the pattern classes. Okay. So, that is the two hops. We first need an algorithm that does well on the examples. So, for example, the perceptron algorithm does well and as shown by the perceptron convergence theorem. On the examples it does well in the sense it separates the examples. Then we have enough IID examples, enough depends on the VC dimension of the hypothesis space we are considering, and in this case the hypothesis space is the set of hyperplanes and we know the VC dimension, we have seen how to calculate the VC dimension for that. So, given the VC dimension, the statistical theory tells us that if you have sufficient number of examples, then a hyperplane that does well on examples, IID examples, will also do well on the test data. Okay. All right. The other main algorithm we considered for learning linear models is the least squares method. Okay. Least squares method simply minimizes this function of W, right. Here for simplicity of notation, we have gone back to the augmented feature vector. I hope all of you remember that instead of writing W transpose x plus W naught, we can simply write as W transpose x by having W naught as the first component of W and putting a first component of 1 in each x, right. That is called the augmented feature space representation. Now, of course, in the least squares algorithm we considered earlier this 1 by n was not there, actually we put a half to cancel this 2 when we differentiate, but any constant here does not change the minimizer of W, the minimizer of J. So, we can think that least squares method actually minimizes this. Why do we write it like this? This is very much in our risk minimization framework. Now, our hypothesis space is a set of all functions that can be represented as W transpose x. So, it is parameterized by the vector W and what we are minimizing. So, now this is nothing but the empirical risk for the squared error loss function. So, this is the output of my function, this is h of x W transpose x h x I, this is y I. So, my loss function is h x I minus y whole square. So, I am using the squared error loss function. Then J is the empirical risk under squared error loss function. So, what least squares method is doing empirical risk minimization on squared error loss function for the hypothesis space of linear functions. Okay. We see in how to obtain the least squares solution that turns out to be A transpose A inverse A transpose y, where A the matrix whose rows are the feature vectors and y the vector whose components are y I. And the least squares method can as easily learn linear regression models. The only difference between the classification idea and the regression idea is that when you are learning a regression function, the y i's are real valued. If you are doing a 2-class classification, y i's are binary valued. If you are learning a general function, y are real valued, except for that we still be minimizing the same squared error, and this is the least square solution. We also seen that we can minimize the empirical risk which is same as JW using gradient descent, right. And we also seen that we can run this gradient descent in incremental fashion, one example at a time rather than considering the entire gradient, and that gives us one more classical algorithm, what we call the LMS algorithm, right. And the adder line, just like perceptron, that is also a very classical model add up to linear element, and that is nothing but minimizing the empirical risk in gradient descent using an incremental version. Okay. We seen that also. And we also seen that least squares method can be learned to can be extended to learn a model G of W transpose x for some function G rather than just W transpose x, right. What is the utility of this? If I am learning any function of x here, in as much as this empirical risk is a good approximation of the expectation, if this is expectation of some G of x minus y whole square, then the best function is the conditional expectation. So, if I am in a classification problem with y is represented as 1 0, then we saw that the best function, the conditional expectation is nothing but the posterior probability. So, minimizing this is trying to learn a posterior probability function, learn a proper function of x that gives me the posterior probability of class 1 for x, and we are modeling the posterior probability by G of W transpose x. Earlier, if you are just using W transpose x, we are trying to model the posterior probability by linear function, which is not a very nice model. So, sometimes if you choose the right G, then G of W transpose x is a nice model class for posterior probability, and by linear least squares method, we can learn the proper posterior probability function and hence the proper classifier. As we seen, an important example of this is the logistic regression, where g is taken to be the sigmoid function. So, in that case of course, because of the g here, we can no longer use the simple linear algebra method of getting a closed form expression for w, but we can still minimize this using gradient descent. Right. So, generally when we use logistic regression, we minimize j by gradient descent or an incremental version of gradient descent. Another important method that we consider for learning linear classifiers is the Fisher linear discriminant, where the idea is that we look for a direction w, such that when the patterns of the two classes are projected onto this one dimensional space represented by w, then the two classes are well separated. Well separated in the sense the distance between means is large relative to the individual variances. Right. Starting with such a objective function, we have seen how to obtain the Fisher linear discriminant, and we also mentioned that Fisher linear discriminant can be thought of as a special case of linear least squares method of learning a regression function with special target values. Normally, when I am running a two class classifier, I think of the target values as binary. We should think of them as binary. I mean, there are still two values, but if I take some special values, then as we see in Fisher linear discriminant can be thought of as special as a linear least squares. So, it is essentially a linear least squares method. Right. So, these are all the set of methods that we have at our disposal for learning linear models. Right. Many of them are very efficient, any of them are reasonably good, and depending on the problem, depending on what you want to learn, we can use any of them. But the problem is all of them learn only linear models, because learning linear models is generally efficient. Okay, these are all nice algorithms. For example, linear least squares has a nice closed form expression, it just involves one generalized inverse of a matrix. Okay. However, linear models may not be sufficient. Right. If I have a function, if I have data x I and y I and want to model the function relationship between y I and x I, right, y as some function of x, a linear function may not be the best fit for my data. Right. So, the best linear function may still be a poor fit. Right. Then what do we do? We discussed this right in the beginning of the course when I was giving you a general overview of what the course is, and there we have kind of intuitively identified at least three broad approaches to learning nonlinear classifiers. What are they? The first one is say, okay, just like we have linear least squares on linear functions are very simple, I can always write them as W transpose x. So, we need a similar way of parameterizing a sufficiently good class of function. The problem with nonlinear functions is nonlinear function is any function that is not linear. Linear functions have a very nice structure. So, linear functions we know how to parameterize, but nonlinear functions are a very heterogeneous class. So, if we can find some good way of parameterizing a sufficiently large class of nonlinear functions, then once again possibly we can use a squared error loss function and minimize empirical risk over that family of functions to learn a good nonlinear function. So, one approach is to look for methods whereby I can get a good parameterized class of nonlinear functions, and over that parameter over that class of functions ask are there some efficient ways of minimizing empirical risk, let us say under squared error loss function. Right. The second approach is to say, okay, next best to linear is piecewise linear. So, try and intuitively break down the feature space, not intuitively, find some algorithms to break down the feature space, so that within each part of the feature space I can learn a linear model. So, I have to learn the partitioning of the feature space and the appropriate linear model together. They are not independent problems, and this way of looking for piecewise linear models is another approach to learning nonlinear models, best exemplified by the so called decision tree classifiers, which we may or may not consider in this course. And the third approach is the kernel function based approach, where the basic intuitive idea is that I first non-linearly transform a feature space into some other high dimensional space and there learn a linear function. As you have seen, what is non-linear in the original feature space can be linear in some other high dimensional space. So, if I can find an efficient way of transforming my original feature space to a high dimensional space and learn a linear function there, then I have learned the nonlinear function to original feature space. These are the three broad approaches. So, first we are going to consider the first approach, right. Learn using a good parameterized class of nonlinear functions, and that is called the neural network models. So, that is what we are going to discuss next. Okay. So, what the neural network models give us? Basically, as I said, we need a good parameterized class of nonlinear functions to learn nonlinear classifiers. So, we are looking at what is a good parameterized class of nonlinear functions, and the so called artificial neural network models are one such class, right. Here nonlinear functions are built up through function composition of the functions of finding linear sums and passing it through a nonlinear function such as a sigmoidal function. So, I keep composing this operation of finding linear sums and passing through a nonlinear function again and again, and that is how I build up many nonlinear functions. Okay. We will see all the details. These models are useful both for classification and regression. As a matter of fact, they are general models of nonlinear functions. So, essentially what they do is learning a function given examples x I, y I, how to represent y I as a function of x, y as a function of x is what these models are for. As we see, even though classifier is a binary valued function, is still a function. So, we can still use a general function learning method to learn classifiers also. So, it is in that sense actually this is a regression function learning model is also useful for classification. Okay. Artificial neural network models are pretty varied, they are a rich class of models. For this course, we will study only what are known as multi-layer feed forward networks, because these provide the kind of parameterized class or nonlinear functions that we are interested in. Okay. They offer a good parametric class of nonlinear functions, and there are some efficient algorithms to learn them. So, essentially they are useful for pattern recognition and regression. So, that is the only kind of neural networks that we consider. But having said that, the neural network models themselves are developed historically with some other motivation. The original motivation not just to find a good parameterized class of nonlinear functions. While that is there, actually the entire field of neural network developed through somewhat of a different standpoint. Basically, the development was motivated by some ideas on the structure of human brain. That is the reason why these are called neural networks. As you know, what we have in our brain are called neurons, that is the basic computing element in the brain, and these artificial neurons are somehow trying to model the structure of human brain, at least that part of the structure of human brain which may be useful for computation. So, historically they are developed as an approach towards engineering intelligent machines. Okay. While that viewpoint may not be strictly relevant to us, since we are studying these models, it is always good to look at that. So, what I am going to do in this class is I will briefly present you this perspective of how neural network models have come up as an approach towards engineering intelligent systems. Okay. So, this is a kind of general introduction to the entire set of models that go under the rubric of artificial neural network models. As I said, we will not be studying all these models, there is rich subclass of models there. We will be only studying one particular kind of models which are useful for pattern recognition ultimately. But in the introduction, we look at the neural network models as an approach to engineering intelligent systems. So, from this standpoint, we can define an artificial neural network as follows. We will start with a generic textbook definition. We think of neural networks as a interesting computational paradigm, that as opposed to the standard digital computer stored program digital computer method that we know of computing, which possibly whose generic abstract model is a Turing machine. As opposed to that, we think of a slightly different way of looking at computation. So, one way we can define artificial neural networks is a parallel distributed information processor. It's a information processor. It's a kind of a computing machine which is both parallel and distributed, and it's made up of very simple processing units. It's parallel in the sense there are many processing units, but each processing unit is not very complicated. It does not have, for example, huge stored program capability, right. It can only represent very simple input output functions, but there are many such processing units. So, it is a parallel processor made up of large number of simple processing units, and as a whole it has a propensity to acquire knowledge through experience. So, basically that is what is useful for us, because as we have seen, all of machine learning is about learning from examples, or most of machine learning is about learning from examples. So, a computing paradigm which puts learning as the cornerstone of all problem solving is important to us. So, that is how the original artificial neural networks are thought of. Parallel distributed information processing processor contains large number of simple units and has a propensity for acquiring problem solving knowledge through experience. So, what is it characterized by? Large number of interconnected units. Each unit implements a very simple function, maybe a non-linear, but very simple. It does not have much of stored program capability. A simple input output relationship is all it has. The units are interconnected, as we said, each of the interconnection has some weight or strength, some parameter associated with it. So, they are called interconnection strengths, and much of the knowledge resides in the interconnection strengths. By knowledge, we mean its ability to solve a problem comes because of the interconnection strengths, not because of the individual processor's input output function. Processor's input output function is fairly simple, but it is the interconnection strengths that can program or make the machine learn to solve a particular problem. Okay. So, the problem solving ability is often through learning. So, it is quite distinct from the way normal digital computing machines are looked at, where the knowledge resides in the program, so to say, by executing a precise sequence of operations, and the particular precise sequence is where the knowledge resides. That is how a generic digital computing machine solves a problem. Whereas here you have a large number of units, they are interconnected, each interconnection has a strength. Each unit itself is very simple, but this interconnection is what gives it the ability to solve a particular problem or represent a particular function. Okay. Yeah, this is somewhat of a different architecture. It does not look like the standard computing architecture. The reason why such architectures were at all thought about is because they are inspired by the structure of the brain. While we still may not know fully exactly how our brain gives us all the capabilities that we have, a lot is known about the structure of the brain, and it is quite distinct from the standard stored program computer architecture that we have. Okay. What is the structure of the brain? In the brain, in the human brain, neurons are the basic computing units. Okay. Our brain is nothing but a highly organized structure of interconnected networks of neurons. Okay. Now, what does each neuron do? Of course, there are many different kinds of neurons, but for our purposes, we can ideally visualize a neuron like this. A neuron is a cell, a biological cell, it is a cell body, and it has input and output terminal, so to say. So, there is one process thing sticking out of the neuron, which is its output terminal, so to say, is called an axon, and it has many inputs coming, they are called dendrites. Okay. So, on the dendrites, axons of other neurons come and make connections, right. These connection points are called synapses. Okay. So, whenever a neuron fires, let us say, essentially when the neuron at its resting is at roughly minus 40 millivolts from the surrounding medium, and for some reason if the neuron's potential increases above some threshold, then the neuron fights what is called an action potential. It is essentially a travelling wave of ionic current, which is let out through its axon. Okay. So, if the potential goes above some threshold, briefly the neuron fires is called a spike, which is a kind of a ionic current that travels down the axon. When it travels down the axon then branches out, or what is called arborizes, and makes connections with lot of input terminals or other neurons, right, the dendrites of other neurons. Each such connection is called a synapse. At the synapse, because this axon fights ionic current, part of that ionic current comes and injects some potential into the receiving neuron at the synapse. Now, the synapses are on the dendrites, and dendrites make a big tree structure on one side on the neuron. So, different synapses can be at different distances from the cell body, the soma, and synapses can be of different types. So, because of that, the amount of charge injected at a synapse will have different effects on the surface potential of the cell body at the receiving neuron. Now, so each of these injected potentials contribute a part to the surface potential of the receiving neuron cell body. So, we can think that the incoming signal is multiplied by some connection weight at the synapse, and that is what gives us the addition to the surface potential of the receiving neuron. There are many synapses, all of them are summated to get the surface potential. If it goes enough, then once again the neuron fights, okay. And this is how it goes on. It is a highly interconnected structure of neurons, and all computing goes through like this, right. So, each neuron is simply, it receives a lot of inputs through its synapses. Essentially at each synapse, because of the inputs from other neurons, some charge is injected into the receiving neuron, and the net effect of all the charge injections at various synapses on its input terminals, which are called dendrites, is a increase in surface potential of the soma of the receiving neuron, and if it goes above its threshold, then it fights an action potential on its own, which now travels through its axon and through the axon orbitalization to all the downstream neurons from, and so on. Okay. Now, this is the generic structure of how simple neurons function. Now, the real complexity is in numbers. In the human brain, they are of the order of about 10 power 11 neurons, that is about 100 billion. Most of these estimates, so say give or take a 10 power roughly. On the average, there are about 10,000 synapses per neurons, at a low of 1000 to a high of 100,000. So, of the order of about 10,000 synapses per neuron, that is the amount of fan in a neuron has, and similar amount of fan out a neuron has. Okay. And so, total synapses taking 10,000 per neuron and 10 power 11 neurons is about 10 power 15 synapses in the brain. Neuron time constants are in the milliseconds. So, as a matter of fact, once neuron files an action potential, it takes some time before it comes back to its resting potential. Till then, it is not sensitive to any other input it receives. So, if you think of this firing of action potential as a switching, then switching time constants of neurons are in millisecond range, okay. Which means a single neuron can send up to about 100 spikes per second. Okay. These are the numbers. Okay. So, essentially, the entire computing is now to be mediated by various neurons sending spikes when they receive inputs, and this coordinated activity is what gives rise to all the intelligent behavior we know. Okay. Because it is a highly organized structure of networks of neurons, it is not just any arbitrary network. Okay. But not bothering about that, just looking at the basic structural connectivity, okay, we can do some simple rough estimates. Let us say each synapse is to be viewed as analogous to doing one arithmetic operation, then we can do 10 power 4 operations per neuron per spike, that many synapses, because it may not be that much, but let us just put a arbitrary estimate. We can send about 100 spikes per second. So, we can do 10 power 6 operations per neuron per second, that is about 10 power 7 operations per second in the entire brain. Obviously, things cannot work at this throughput pace, it does not, because there are so many of your neurons are meant to keep your metabolism going, keep your heart going, keep your body posture going and so on, right. But and there are many neurons in your eye and retina and so on. So, there is a lot of sensory neurons, lot of motor neurons, okay, which are needed for the organism to function. But still, this is a staggering amount of operations possible if if we know if all the neurons are working in concert. So, this is something that all of us know. Massive parallelism can deliver massive computing power if only we know how to manage it. Of course, one does not know how to manage a 100 billion process to act together, right. But having said this, then one can ask, okay, it seems to be a very simple structure. Each neuron has very simple input output behavior, and somehow the entire power seems to be the way in which they are interconnected and made to work in concert. So, shouldn't we try and think of computing system architectures which somehow mimic this? Okay. So, here is a dramatic way of saying this. If you look at detailed computers, they are very precise design. Of course, you use very sophisticated software to design the chip layout. They are highly constrained, not very adaptive or fault tolerant. If something goes wrong with the chip, that is the end of it. Mostly centralized control, mostly deterministic, and have basic switching times of the order of nanoseconds. Whereas the natural neural networks are massively parallel, they are highly adaptive and fault tolerant. Neurons keep dying. We do not have many bone marrows where new neurons are made. At the current knowledge, we think if at all just a very small fraction of neuron regeneration grows, most of the neurons that we are born with only die. Okay. But in spite of it, we have a lot of adaptation and a lot of fault tolerance, of course. They are self-configuring, self-repairing, noisy, stochastic, and have basic switching times of only 10 power minus 3 seconds. The switching times are milliseconds. And what is important is that it is not pre-programmed. Most of what a person of 5 or 10-year-old can do, almost 99% of the capabilities of 5 or 10-year-old person are not there at birth. Right? When you are born with your neurons, you cannot even do very simple things like sitting up or standing and walking. Right? So, most capabilities of our brain are all learned. Right? So, not only it has very strange architecture, but it essentially relies on learning. Given that neurons input output structure is very simple and already well constrained, it looks like the only thing that we can learn not synapses. Maybe we form new synapses or we modify existing synapses. So, essentially synaptic strength might be what change when we learn. Right. So, essentially is the interconnection strengths that translate into having learnt a particular capability. So, whatever knowledge resides in the brain must be that of interconnection strengths. Okay. This is actually was first propounded as a theory or hypothesis by a famous psychologist called Hebb, when he wrote a book in late 40s called Organization of Behavior. The basic premise is very simple because neuron function seems to be very straightforward. There is not much scope there for doing something drastically different, but the behavior of a 2-day-old human being to a 5-year-old human being is so different that there must be something that has changed in the brain, and most probably what is changed are all the synaptic strengths. So, all learning is in terms of changing synaptic strengths. So, now stepping back a little bit, if we think of the field of artificial intelligence, of course, artificial intelligence today means one particular set of techniques, but let us not worry about it. Let us think of it in the sense of what the name suggests. Its grand goal is to understand intelligence in computational terms and develop machines that are intelligent. Everything we put in quotes, so that let us not get into any philosophical arguments. Let us not define what a machine is and what intelligence is, but that is irrelevant. But within the context of what all of us understand, artificial intelligence is about understanding intelligent behavior in computational terms and developing machines that are intelligent. Historically, today we can say that there were two distinct approaches that people followed. One may be called the symbolic approach, where the idea is to develop models for intelligence in terms of processing symbols. Right? The idea is that the resulting methods or algorithms may not resemble how brain does anything. As a matter of fact, we may not even understand how brain does something, but if you understand what computation is involved in a particular intelligent behavior, then we can simply try and create it through some symbol manipulation. The second is to say, well, we do not know how the brain actually achieves its function, but we know a lot about the brain's architecture. So, let us try and mimic the architecture of the brain and then ask, does it lead us to a kind of machine that have some interesting behavior. The first approach can be called the symbolic AI approach. The basic idea there is that the brain is to be understood in computational terms. So, maybe brain is to be understood only in computational terms. That is, if I look at any intelligent behavior, speech, language, natural language understanding, common sense, all of it is some kind of computation. I may not fully understand what kind of computation it is, but nonetheless I can think of it as just a computation, and any computation can be done on a Turing machine. So, essentially any machine that is capable of carrying out abstract computation is capable of exhibiting intelligent behavior. That is the basic idea of the symbolic AI approach. This is often reified into what is called a physical symbol system hypothesis. What the hypothesis says is that any physically realizable system that is capable of creating, storing, modifying abstract symbols is in principle capable of intelligent behavior. Right. So, essentially intelligence is that you symbolically represent the world outside, right, through some symbols inside, and define proper operation of the symbols to represent, whatever inferences you want to make, or whatever changes in the outside world that you want to track, and so on. So, any such system which is capable of creating, storing and modifying abstract symbols is capable of exhibiting intelligent behavior. Since a detailed computer is a universal symbol manipulator and it can in principle be programmed to be intelligent, right. That a detailed computer's architecture is vastly different from the brain's architecture is really irrelevant, because brain is one way of representing one physical system that can represent abstract symbols maybe. Detailed computer is another kind of physical system that can represent abstract symbols. So, as long as the system has the capability to manipulate abstract symbols, it is capable of intelligent behavior. So, we have to just figure out how to understand any intelligent behavior in computational terms, so that we can program it in a detailed computer. This is the basic symbolic AI approach. Of course, it has given rise to a lot of interesting applications, expert systems, chess playing programs, all of them come out of this symbolic AI approach. Okay. But something that characterizes the symbolic AI approach is the faith, the dogma, the theory, the hypothesis, whatever you want to call it, which says that the architecture of brain per se is irrelevant for engineering intelligent artifacts. That the specific architecture of the brain is some accident of the evolution. So, it is not necessary that such an architecture is needed for intelligent behavior. Okay. And this is the faith and symbolic AI approach, where we are discussing it only to contrast with neural networks, right. We are not saying right or wrong or which is better, those are unnecessary philosophical debates, but this is one approach. The other approach, which we are more interested in, is the artificial neural network approach, which is another approach towards understanding brain or building intelligent machines, an approach characterized by mimicking the brain at an architecture level and trying to see within that architecture, can we think of some simple learning algorithms which will allow us to solve some problems, right. So, it represents a computational architecture inspired by the structure of human brain or structure of mammalian brain or structure of any intelligent organism's brain. So, it gives rise to computational methods for learning dependencies in the data streams, right. There are many interesting things, just like expert systems on the symbolic AI side. There are many interesting applications came on this, system identification for pattern recognition, so on. There are some interesting methods of learning using these structures. The characteristic of these structures is that there are emergent properties, that is, there are some properties of the entire structure which cannot easily be assigned to any subunit. So, the network as a whole has some interesting properties which cannot be said that it is the synapse that has the property or the neuron that has the property. Okay. The other interesting aspect of these models is because they are built of very simple processing units and everything resides in the connection strengths. Learning is the only way to program them. So, we have to somehow find the weights, and the only way we find weights are through learning. Okay. Whether artificial neural networks really gave rise to understanding biology is a difficult question. I'll come back to it in a few minutes again when we finish the discussion. But most of the models that we are considering here can be thought of as mathematically purified neurons, right? They are not sufficiently realistic in terms of real biological neurons. They can be thought of as very simple mathematical models. So, we can think of them as models of mathematically purified neurons, and in that sense the specific models we consider may not have much to do with modeling biology. Okay. So, we can now sum up the discussion. Artificial neural networks are computing machines that try to mimic brain architecture. So, what do they have? Large number of interconnected units, right? Each unit is like a neuron, that is why they are called artificial neurons. Sometimes people omit the word artificial, but at least in the beginning we will use the word artificial. Each unit has simple input output mapping like your neuron firing an action potential. So, essentially it takes some weighted sum of its inputs and passes it through some function to get its output, right. So, each input is a very simple input output mapping, and they are interconnected, and each interconnection has a numerical weight attached to it. It is like the synaptic strength in the real neural networks, and the output of a unit depends on the outputs and connection weights of units connected to it. Each unit receives inputs from many other units, it is an interconnected network of units, and the output of any unit depends on both the outputs of the units that send their outputs to you, as well as the weights that connect those outputs to this unit. Okay. The knowledge resides in the weights. Essentially, if you want the system to do anything, the only thing you can change are the weights. The functional relationship of how output depends on the weights is prefixed, but you can change the values of the weights. So, the knowledge essentially resides in the weights. Okay. That is the kind of structure that artificial neural networks give rise to. And the problem solving ability hence is often through learning. So, because there is a large number of weights and it is impossible to analytically decide how the weight should be, or impossible to get closed form expressions for how weight should be, much like in what we are considering so far in pattern recognition, the problem solving ability often comes through learning. These models we have already seen actually, right. We can think of a single neuron model like this. Okay. There are many inputs, say x1 to xn. Each input is connected to the neuron through some synapse. So, that interconnection has a weight, so called Wi, and y is the output of the neuron. So, what does the neuron do? It calculates its net input as a weighted sum of inputs, right. So, this is input coming to the neuron. So, multiply that with the weight and sum over all the inputs, that we call the net input, and you calculate your output as some function of the net input, where f is called the activation function. Okay. This can be a simple model of a neuron, right. We have seen such models already in pattern. Perceptron is a very simple model. When we studied perceptron, I actually said that it comes from some simple neuron models. So, essentially if I take this activation function to be a step function, this is exactly what the perceptron does. It takes the weighted sum and thresholds it at some point. So, if the net input is greater than some threshold, output is 1, net input is less than the threshold, output is 0. We can think of this as these are the incoming charge injections into the neuron, these are the synaptic strengths. So, at the soma the net input represents the total increase in potential, and if it is above some threshold, you fire your own action potential, right. So, but viewed simply as a mathematical model, within this structure, if I take f to be a step function, I get a perceptron model. If I take f to be a linear function, we get that adaptive linear element model, which is what we said is the original LMS algorithm is based on. So, these models, as I said, already are used in pattern recognition. At that time, we did not talk of them as neural network models, but these are what we consider as our linear models can be simply thought of as single neuron models. Okay. But really the reason why the neural networks are more powerful is that you can interconnect them. We can connect a number of such units to form a network. So, when you say network, what means is output of one neuron can become input to another neuron, like this. So, if I take neuron 3, it takes inputs from neuron 1 and 2, calculates its output, call it y 3, and that itself now forms inputs to neurons 5 and 6. Right. So, in this diagram the notation is y j is the output of the jth neuron and w I j is the weight of connection from neuron I to neuron j. Do not read anything into the bold characters. The weights are in bold only because the diagram is crowded, and if I did not put in bold, it was becoming very difficult to notice them. That is the only reason the weights are put in bold. So, in all my diagrams, a symbol being in bold means nothing. Okay. So, again, so y is the output of jth neuron, y j is the output of jth neuron, and w I j, that is our notation. So, w 1 3 connects neuron 1 to neuron 3, w 3 6 connects neuron 3 to neuron 6, and so on. So, essentially if you take this neuron, it gets some input from other neurons, calculates output. This output itself now forms input to some other neurons, and so on. So, there is a network like this. Okay. How does this network compute? Each neuron computes weighted sum of inputs and passes it through an activation function to compute its own output. So, for example, if we go to neuron 5, how does neuron 5 calculate its output? It takes output of neuron 3, multiplies with w 3 5, output of neuron 4, which is y 4, multiplies with w 4 5, and passes it through its own activation function. So, y 5 is f 5, the activation function neuron 5 of w 3 5 into y 3 plus w 4 5 into y 4. Right. Now, how are y 3 and y 4 obtained? They themselves are obtained the same way. Y 3 is obtained by multiplying y 1 with w 1 3, y 2 with w 1 4, y 2 with w 2 3 and passing it to the activation function of y, and similarly y 4. So, if I expand that, this y 3 and y 4 can be expanded to y 3 becomes f 3 of w 1 3 y 1 w 2 3 y 2, and y 4 becomes f 4 of w 1 4 y 1. So, as you can see this output is now a function of all the weights and here the inputs y 1 and y 2, and these are obtained through composition. So, I have linear sum and some activation function. Now, once again a linear sum over such things and an activation function. So, I use composition of linear sums and nonlinear activation functions to build more more and more complicated functions. By convention in networks like this, we take these are the input neurons, we will look at the full notation later on, but essentially for the input neurons its output will be input. So, it is just a fan out device. So, we will take by convention y 1 is equal to x 1, y 2 is equal to x 2. So, the expression we wrote for y 5 directly gives y 5 as a function of the inputs x 1 and x 2. Okay. So, that is the if I take y 1 is equal to x 1, y 2 is equal to x 2, y 5 is a function of x 1 x 2. It is a kind of nonlinear function because the f 3, f 4, f 5 are all nonlinear. The w's are all the parameters of the function. Okay. So, x 1 x 2 are inputs, y 5 y 6 are outputs. So, that particular network model represents some function from R 2 to R 2. Okay. So, a single neuron, as we seen, because it only one output, represents a class of functions from some m inputs to a single real output R m to R. Specific set of weights realize specific functions. Right? Your perceptron can represent any hyperplane. Which hyperplane it represents depends on what weights we put on the perceptron. By interconnecting many neurons, we get more complicated functions now from R m to R m prime, right. We have seen an R 2 to R 2 function network. So, we can get more complicated model that can represent functions from R m to R m prime. the architecture of the network will of course constrain the function class that can be represented. We will look at it later what kind of architecture can represent what function classes, but the architecture in some sense is reasonable to assume that constrains the class of function that can be represented. Whereas specific weights define a specific function within that class. And finally, to form meaningful networks, nonlinearity of the activation function is important. Look at this function. You suppose f3, f4 and f5 are all linear functions, then f3 of this is some linear function of y1, y2 which is x1, x2, f4 of this is some linear function of y1, y2. So, I can write the whole thing as a linear function of x1, x2. Now, if f5 is also linear, the whole thing is a linear function of x1. So, essentially it represents no more than what a perceptron can. Even if f5 is non-linear, if f3 and f4 are linear, what is inside here is simply a linear sum, a linear function of x1, x2 on the weights. So, essentially its representation capabilities are no different from what a single neuron can represent. So, nonlinearity of the activation function is very important. Typical activation functions used in these models are things that we already seen. One is what is called a hard limiter. Essentially, if the net input, the argument to the activation function is greater than some threshold, then output is 1, otherwise it is 0. Of course, as we already seen in the percent case, I can always take tau to be 0 by pushing tau to the input side. Okay, we will see that later on. Another activation function that we see is the sigmoidal activation function. So, the hard limiter is not differentiable. So, sometimes it may give us problems as we shall see later on. So, we can make that into a nice smooth differentiable function, that is a sigmoid. This is some 1 by 1 plus exponential minus bx. I can always scale it to a, here a is actually 2. This is the rough shape of it, and the coefficient b determines the slope of it near 0. The sigmoidal function takes only from 0 to 1. So, it cannot take both positive or negative values. If I need to take both positive or negative values, I can take hyperbolic tangent, which has roughly the same shape as sigmoid, but goes from positive to negative. Once again actually goes from minus 1 to 1, but I can put any amplitude there and also I can put a parameter b to control the slope near 0. So, these are the 3 most often used activation functions in neurons. Okay. Now, why does one study such models? One we already seen, a belief that the architecture of the brain is somehow critical to intelligent behavior. So, if I mimic the architecture and sees what models of this architecture can do, it may tell us something about how intelligent behavior may come about. The models, as we see, implement highly nonlinear functions. They are adaptive and can be trained by learning the weights. So, it gives us a good class of nonlinear functions that is useful in many applications, time series prediction, system identification control, and most importantly for us pattern recognition regression. There can be a third goal. Models can help us understand brain function. So, actually I can put models like this, then tweak them to be realistic to some specific neurons in terms of how many synapses they have. Maybe I can put some nonlinear synapses and then try to see what the model predicts, and then go back to experiment, see if it can be observed in real neural tissue, then once again tweak the model and so on. As a matter of fact, there is a field now goes and named computational neuroscience or theoretical neuroscience, which actually does this, and they do much more sophisticated models of neurons than what we considered. They actually take care of a lot of nonlinearities, a lot of models for how the potentials are transmitted through the neuron, through the dendrites and so on. So, there are methods of using such models as a way of understanding brain function. Okay. So, of course, we are not interested in any of this, as you already said. We are just interested in these models as some nice parameters class of functions for doing pattern recognition regression. Of course, as the network that we consider is only one simple model. It can be called a feed forward model because there are no feedback connections. Okay, let me come to feedback later, but let us ask what are all the possible models we can think of. One is where the models work in discrete time, continuous time, all the units change, compute their outputs together in a clock fashion like a digital computer, or everybody does at some random time of their choice, where the activation function is deterministic, stochastic. This is one kind of choices we have. Where choices in terms of architecture, where the interconnections are only feed forward or also having feedback, whether the outputs of units are binary, they take only finitely many values, they are continuous functions. There are many different combinations, and all combinations are possible. Right. So, for example, here is a simple network, the rest of it looks like a previous network. You consider the outputs go only in one direction, but output of some unit can come back. Right. So, we can think of this as using Z inverse as a usual unit time delay symbol. What it means is the output y at time k is some function represented by the network of some input x 1 k, another input x 2 k, and y of k minus 1. Right. So, this can model a dynamical system. So, many of these models are used for nonlinear dynamic system modeling also. Okay. Because as I said, we considered only feed forward networks, which provide a general class of nonlinear functions. Right. By feed forward, this is the network model that we considered last time. So, each neuron calculates its output and sends it to downstream neurons. There is no feedback connections. Because there is no feedback connections, we can always organize them as layers, such that a neuron in one layer gets its inputs only from the immediate previous layer, sends its outputs only to neurons in the next layer. We can always do this, a little thought will tell you, because if suppose neuron 3 has to also get neuron 2's output, I can simply put a dummy unit here, which only gets neurons 2's output and then passes it on to neuron 5. Right. So, by adding such dummy units, if I need, I can think of this network always having a layer structure. So, I call this layer 1, I call this layer 2, I call this layer 3. Any neuron in any layer gets inputs from the immediate previous layer and sends its output only to the immediate succeeding layer. Okay. We call the layer 1 as the input layer that takes inputs from the external system, last layer as the output layer, which sends its outputs to the external world. Everything in between is the hidden layers. So, this we call hidden layer. Later on I will tell you why the name hidden. Okay. So, this particular network represents some class of functions from R2 to R2. It has 2 inputs and 2 outputs. So, if I put this entire thing into a black box, it has 2 inputs, 2 outputs. It represents some function from R2 to R2. Right. Each unit can also have a bias input. Okay. So, earlier we only considered this, but we can have y as a function of w I x I plus some bias w naught. We can always think of bias as a extra input, because I can make the summation going from instead of 1 to d, I can go it from 0 to d and call w 0 the weight and an extra connection, which is permanently connected to an input that is permanently kept at plus 1. So, I think of x 0 as a extra input, which is permanently plus 1, and I can represent it as a bias input. Okay. So, in general, we can have feed forward networks like this. So, what we are going to study next class is, now we will forget all about intelligent machines and everything. We will just look at this as a nonlinear class of functions. So, there are layers. So, each neuron computes its output and sends to a succeeding layer. So, using, and we can have many number of layers, many number of things. So, using such models, we will ask how we can represent and learn nonlinear functions that are useful in pattern recognition regression. Thank you.